have my charger ready? And they're all like, no. So this guy, God bless him, spent 20 minutes in the back trying to find it, another 10 minutes in the front trying to find it. And I said, okay, so if you were me, what would you do? Say you need this first thing in the morning, what would you do? His response is, well, I'd go look on the shelf. I said, I did that. He said, we could go to Alpharetta. I said, okay, I'll go to Alpharetta, but can you see their inventory? Because I don't want to go to Alpharetta and have this happen. And he tried for like another 10 minutes to call Alpharetta, and they wouldn't answer the phone.
What is this?
So it's a flash drive if you ever need it. So then I had to go down there, fingers crossed. Walked in, they had like 8 chargers for the Surface Pro out on the display. Grab one, come home, cancel the other order. But it was maddening. So be very careful. I don't know that anybody stepped on it. I don't know what happened to it. But if you see it, it's gold. Step around it.
There's a micro center in the loop.
Yeah.
Mm-hmm.
Mm-hmm.
That's how Mike is like, you're always like very, very, very careful about the charger. And then it breaks, and I'm over here just like throwing it around.
Yeah, you're
using it as a whip against
slightly crazy.
Ardelia, broken yes.
Savannah, Eleanor. So
I always avoid the charger and then
Eleanor's that one.
Like run into something.
Jackson is not there. Please.
Like this.
All right, this is the one, Eleanor. I think we should do this one again. Let me talk to you about it because you missed some parts. It just was missing. They were just blank. So I think we should. Let me talk to you after class. I'll give it back. Drew, Jack.
Yay.
There's another Jackson. Don't share your grades. Lily, Savannah, Sky. I'm handing them out to you today. How was the wedding? Would you like to share? No.
No, not really.
She had a wedding. It was
There
special.
was nothing really, like, I don't know, we danced for a couple hours.
That's always fun, isn't it? I love that. That's the best part is the reception. The reception's
I
remote.
got the point.
A cat? Okay.
Mysteria, did I not turn my
Yeah,
You weren't here.
Oh, I was.
Remember? Yeah, you were home with your mom.
I got Christmas nails.
Those are fun. Oh, those are super cute.
I got Christmas nails as well.
All right, let's
Yeah,
see.
the same thing as Christmas nails, Halloween nails, nails for every season.
So couple
right?
things. All right, Drew, if
If
I can have your attention for a minute, guys. Hey, Delia. All right, let's see. Couple things. Let me share screen here so anybody who's not watching it can see. All right, no, it's Drew, shush. All right, I wanted to tell you real quick, I am working on, hang on, wait. I am working on the next 9 weeks worth of lessons to give to you at Christmas. And I promised that I would have all of them ready, but now I'm like, I will definitely have your syllabus ready. I will probably, there may be a couple of lessons that I'll give you when you get back from break, just because it gives me like 2 more weeks, 3 more weeks to do some typing. Especially since I lost all of yesterday trying to find a charger, which was so fun. I mean, it was dead, like dead. So let me just tell you real quick what's coming for you guys, all right? All right, so just a reminder that on the last day of this semester, which for us is the 17th of December, which is only like what, 3, you count this one 3 classes away? It's almost over, we're almost there, guys. That's the day you're gonna come in and you are going to do your midterm that day, right? Now it's like a quiz for you guys. It's not too terribly bad. It's not weighted more heavily than any of your other tests.
What does that mean?
But it's, okay, so what it is it's a cumulative test that goes from day 1 until the end of the semester. So it's everything we've learned, not just a chapter or a unit or a lesson. It's all your lessons. Now, if you go to your Dropbox file where I keep all the stuff, if you go to Dropbox, there is a review. It's a PowerPoint right now. Does anybody not have PowerPoint?
But I don't think.
Okay, I'm converting it to video. I just haven't done it yet. But there is a PowerPoint, and I'm going to try to go over it a little bit with you guys in class until then, so that you get a little more used to it. But it covers everything that's on the midterm quiz, everything that's on it. Okay, so everything, you'll know what it is beforehand. All right, so then that day what you're going to do is you're going to come in and you're going to have, you're going to actually have like 2 quizzes. You're going to have your weekly quiz like you always do, your weekly test, but that's going to be due on Monday online. instead of Tuesday online because I want that done before you get here. So basically it's just bumping it up one day, which isn't terrible, right? And then you're going to come into class and you're going to have your in-semester test, in-class quiz. And it's going to be like, so you're going to get here from 10 to 10:45, which is your normal class time. You're going to do that quiz. And then we're going to start our movie, which is October Sky.
What's October Sky?
It's a really cool movie. It's a movie about some boys who do rocketry, basically.
Rocketry?
They're inspired by the space race between the United States and what was then the Soviet Union, and it's really, really kind of cool. It's a very cool movie. But there's a lot of physical science in it.
For Back to the Future for the next.
It's always a good one.
Yeah.
So have a look at your syllabus. Flip ahead. I did. I should disown her. So listen, flip ahead a little bit so that you know what's coming. All right. Be looking ahead. Also notice that for that day while we watch our movie, it's a party. Okay. And that party, we're gonna have. If your birthday is January to March, you bring something sweet. April to June, you bring something salty. July to September, you bring something savory, and October to December, bring something healthy.
Wait, what was the day you bring something salty?
That was April to June.
What was the sweet?
Sweet is January to March. Okay. It's in here. It's written down. It's in your syllabus. So
What's the syllabus? What's
you know
What
where
should
you've
I
got
bring?
your lesson plans at the very beginning of your binder.
What should I bring?
I don't know, whatever. So anyway, here's what I want to cover. When you get back, do I have everybody?
Yeah.
All right, when you get back, you come back to class on the 7th of January, okay? We're going to cover waves and then sound the following week on the 14th. Then we're going to go to electromagnetic spectrum on the 28th. Oh, sorry, I skipped one. 21st, electromagnetic spectrum, and we continue that on the 28th, 2 weeks of that. Then we've got the 4th of February is light. And then the 11th of February is magnetism and electromagnetism. Okay, so it's some really cool stuff next semester. Then the 18th is electric charges and currents. And the 25th of February is electricity and magnetism. This will be really fun. You have really cool labs too.
Can I go
Like,
get my pencil?
yeah, do you need it? I have some. Oh,
looking at?
where's my little bins over there. Go ahead and grab whatever you need.
Because I was across from you.
And then let's see. On the March 3rd, it's electronics, followed by on the 10th, introduction to, now this is where it changes, introduction to matter, solids, liquids, and gases. Okay, so now what's going on here? Now what's going on here is we are moving into our chemistry units. We will have completed our main physical science and we're running into chemistry. Do you remember at the beginning of the year, we had like several weeks where there was like a whole chapter and it was a lot of reading, but then we covered it very high level instead of like we've been doing for the physical science stuff. The chemistry stuff's gonna be like that, okay? After that, we have one more class before spring break, and that one covers chemical bonds. Then it's spring break, and then we come back, and this is when it gets very, very interesting because we only have a few more classes. We've got a chemical reactions and acids, bases, solutions, and then we have one more class with carbon chemistry and exploring materials, and that is lesson 35. Lesson 30, and that is on April 28th. Now, lesson 36 is 3 weeks long. It's May 5th, 12th, and 19th. And it is the Rube Goldberg competition.
Right?
Yeah, it's the Rube Goldberg competition. So listen, so basically on the 5th, you're gonna collaborate, brainstorm, design, begin construction. All of these days, your class time is different. It's just 10:30 to 12:30 for everybody, for the whole class. All levels, it's just lab groups at that point, okay? And then you come back on the 12th and you continue your construction. The 19th, you finalize and run your machines. After class on the 19th, if you want to go to the pool, we can go to the pool. But if you're under 13, you have to have a parent with you. Pack your snack, pack your lunch, whatever.
Wait, what?
We can do the pool. But here's the thing. If you, and that's the 19th of May, but if you, and it's all going to be printed out for you, if you can complete your Rube Goldberg stuff by the 12th and run all your machines on the 12th, then we can go to the pool and be done and not come back on the 19th. It's like one day. day less. Yeah. Okay.
That's the goal.
So yes, ma'am.
When was the pool thing?
It's either the scheduled for the 19th, but it could shift up to the 12th of May.
Is your Goldberg machine gonna be
Mhm.
outside?
Yeah, outside. Yeah.
Question. What's the
When we go to
Goldberg
the pool, do
machine?
you count as an adult or do I have to bring my mom?
I count as an adult, but your mom should be there because I can't watch that many people at one time. Plus,
I'm a good
The
swimmer.
machine
You don't
is
have
a
to
bunch
watch
of
me.
machines like gears. and
technically,
buttons,
if
and
I
we
have,
time to make something simple happen,
yeah,
I've never
like
done
having this
in my whole
thing
life.
roll over and
It's
put
a
something
it's a
else
series
in
of
it,
simple
and
machines.
which makes it hit a bunch of dice,
So-
and
Transfers
something-
energy.
Technically, we're like the pool.
Yeah,
Yeah, like
transfers.
dominoes.
And then like it makes something else swing, which hits something else, which puts this.
It's
thing
a
on
really
a
complicated
scale,
thing
and
to
then
do something really simple.
All right.
And it just goes on.
Okay, so let's get to our notes. Everybody, open up your notes for today. Yep. Today is the 3rd.
We once did one where it was we turned on the hose and then it filled up a
It was
bucket,
very cool.
which made a little thing go down, and then when it went down, it pushed this little pulley system which went up and then knocked another pulley system down a track and then it hit something and then it turned over and put out a fire.
It was cool. It was very fun.
Wait.
All right, so it did put out a fire. We did. That was a goal. So, all right, here's what we're going to do. We are starting our energy and power unit today. Drew, my turn. So, energy and power today is what we're going over, all right? And let's see, you guys started talking about different types of energy. So, I brought these things down here. Does anybody know? It's Dusty. Does anybody know what this is called?
Adam's cradle.
Not Adam's cradle. What is it?
Newton's cradle.
It's a Newton's cradle. Okay, so this is a Newton's cradle, and let's see, this guy right here.
Could I explain how it works,
So-
please? I know how it works.
Hang on. Let's see who doesn't own it. I'm gonna put it right here so we can see it. Who would like to
Explain how it
guess?
Can I explain
Yeah. Sure, hang on. Let's let Trav give it a shot. Okay, Lily, I'm shifting it so I can see it in my camera. Because Jackson's not here and he may want to see what was up. Hey, Jackson. All right. Do you want to give it a shot, Trav? How does this work?
So you pull one back. Do we do it? Or, yeah.
Yeah.
So you pull one back,
It's the balls. Uh-huh.
and all the energy transfers just and like pushes one out. all the time.
Very good. Very good. So when you pull it back, Lily, lift one up for me on the end. So when you pull it back, what kind of energy are you giving it?
Potential
Wait,
energy and it transfers
Let hands go up. Go ahead. It's
Potential.
potential energy, right? What kind of potential energy?
Potential.
There's two types. Gravitational, Jack. Good job. Okay. So Lily, lift it up real high. And well, not that high. Hang on. Okay, now drop. All right, Drew, what did you want to say about it?
Can I try it? Okay.
Yeah, sure. Hang on, let me
So,
top for a
could you
second.
turn it over? Billy, could you pass it?
This thing looks like a carnival.
So when you lift it up, it turns this into, this is kinetic, potential energy right here. And as you let go of it, it becomes transferred into, it transfers into kinetic energy. And it hits here, the kinetic energy transfers through here until it has nowhere else to go. And then it hits this one back out.
Right.
And then the same pattern happens until friction stops in a minute.
That's what I was waiting to hear. All right, excellent. Pass that back. So I was going to say, will that go on forever and ever and ever?
No.
No. Friction will stop it, right?
Air friction.
Yeah. And so
Voltage friction too, right?
is the energy that, so when Lily lifted the pendulum up, she used energy, right? Now she created some gravitational potential energy, but where did her energy come from? Where did your energy come from, Lily?
My hand.
Your hand. Where did your hand get the energy? What moves in your hand?
Muscles.
Your muscles. Where'd your muscles get their energy from?
Your body.
Yeah.
Your mom.
Your brain.
What'd you have for breakfast, Lily?
Your mom.
Nothing.
Your mom.
You didn't eat? What'd you have for dinner last night?
Nothing.
Hold on.
I had a bowl of
I
cereal.
don't have it.
Hang on.
Wait, that's not really
Let's pretend you ate pizza for argument's sake. All right, if you ate, oh no pizza,
She
okay.
doesn't like pizza. She's strange.
Oh, that's right, you're
Spaghetti.
weird like that.
cheeseburgers.
Tacos, Lily. Let's pretend you ate tacos. Okay, stop. All right, so listen. So if you ate the tacos, you got energy from the food. Now, where did the beef that you ate in the taco come from?
A freaking cow.
A cow.
Oh, I know what I had.
Oh, what'd you have?
I had stir fry.
Oh, okay, stir fry. Was it chicken or
I'm in the kitchen making stir.
chicken stir? Okay, where did the energy in the where the chicken came from? A chicken. Wait a minute, Drew. I'm asking her. Where did the chicken get its energy from? Whatever it ate, right? Okay, so whatever it ate, the chicken got its energy from. What do chickens eat?
Corn.
Chickens eat like anything you give to them, no joke. Our neighbor here used to have chickens, illegal, they're not allowed in our neighborhood. Yeah, we would throw, like, you cut up celery and you chop off the end, we would throw that over there and those chickens just devoured it. So chickens will eat anything.
Even
So let's say, no, but let's say the chicken ate only
they're
corn.
herbivores.
Let's say the chicken ate, well, they're omnivores actually. Let's say
Wait, they eat meat?
they'll eat bugs, worms.
Oh, true.
Let's say the chicken only ate corn. Where did the corn get its energy from?
Corn. Water.
The sun. So nearly every source of energy on Earth is going to come from the sun. Gravitational potential energy,
Not water.
whatever energy it takes to get stuff up. That's what I was saying. Stuff that involves gravity is one thing. But even if you're, like right now, our house is being heated, right? Our house is being heated and we have natural gas. We have natural gas. Natural gas is a fossil fuel, right? It comes from decayed and fossilized matter. So dinosaurs essentially, so they got their energy from the plants they ate, or the dinosaurs they ate, which got it from the plants they ate, and it all came from the sun. So that's where almost all of your energy comes from. Yes, Drew, one more question, then we're gonna go to lesson.
It's actually a statement, but did you know the gas that comes from the fireplace is almost over 1 million years old?
Oh yeah, it's very, very old, way over 1 million years old. So
Well,
this real quick, just so you know, I brought this out because it's a bit of a little trick here. There's no such thing as a machine that is a perpetual motion, right? It's impossible for a machine, perpetual meaning forever and ever and ever not stopping. Friction's always going to slow it down if something else doesn't.
Unless it's in
The reason this is continuing to go is because there's what? There's a magnet in it, right? Okay, so there's a little magnet in here. It's down here in the bottom. And this is magnetic too. And that's either a push or a pull every time it comes by. So when you see things like that, that's what's going on. And also, they can do all kinds of stuff with magnets, like move more than this. I've been in a train that was moved by magnets, so pretty impressive.
Oh, you missed me. I found a brownie for me.
Oh, did you? What'd you find?
It's TH instead of a.
I noticed that.
Where's that?
I found something.
Really? Oh, in mine it says the. Okay, glad you found
I
that.
made
Okay.
jokes about Donald Trump when he went to that meeting.
True. Yeah.
Where?
I don't know.
You're gonna explain.
All right, let's look at our notes, okay? We're gonna look at our notes, and there's this weird little experiment in your book that I'm not understanding. Yeah. Which question?
I found a brownie point in the test.
Oh yeah, there was a good one in the test. At least one.
It was he instead of the.
You found a he instead of the. Yeah, there was one.
Yeah.
There was one.
That's in it. My dad caught some few mistakes.
Yeah, that's good you catch them, because then I go back and fix them. But what was really entertaining to me was there was one in the Lab Rats group that actually said typo instead of type, and I was like, that is the most ironic brownie point of all time.
How many brownie points are
I think you guys are at like 22 now, so I'm thinking what I'll do is I'll just provide like extra brownies and cookies at our Christmas party, because I think everybody's going to be caught up with it. That's on the 17th. All right, so notes open. We got to go through our notes.
Okay, I need to catch up on it. I need to write
You got to look through. All right. Do you have your notes or you don't have them? You do? Yeah, that's it right there. You're looking at them. All right. The ability to do work or cause change is called what? Anybody know that one? The first blank. Energy. Savannah's with me. Here, use that one for
It
now.
was already filled in for me. So
Was
I
it?
wrote it down. Yeah.
Okay, yeah, that one was
Yeah,
filled
I
in.
had to do
Okay.
some questions.
Yeah, I know. See, I do mine first, and then I go back and delete mine to make
I also
yours.
noticed something
I
else
know.
happened on mine.
Yeah, it's,
Every single question
Had an
on
answer.
mine was
Yeah.
answered.
that's my mistake. I missed it. So that's
So,
the other
like-
giant brownie point of the day. All right, energy comes in many different forms and from multiple sources. You can think of work then as a transfer of energy. The two main kinds of energy are kinetic energy and potential energy. So, Eleanor, let her focus. You focus too. Kinetic energy is energy of motion, right? The kinetic energy of any moving object depends on its mass and speed. All right, guys, look right there at the formula. Okay, do you see it in the little box? The box on the right, it says kinetic energy. And it says kinetic energy is the energy that objects possess due to their motion. And then you have a formula. If you were to replace the letters in that formula with the words that they mean, what would it say? Who can read it with the words? Anybody want to give it a shot? Okay, so it would read kinetic energy equals 1/2 mass times volume squared. Does everybody see how that works?
Yeah.
Because KE is kinetic energy, and that's measured in joules, see the J? And then you have mass, and that's measured in kilograms, and velocity, which is measured in meters per second, right?
I have
you
a
go.
question. Why does
Yes.
somebody use newtons when they're talking about weight?
Force.
I know, but you can also use newtons as a measure of weight, right? Because I mean, like this, you could say, you know, it has force pushing down on the paper.
Sort of, but yeah. Can we come back to it and go back? Can we refocus here for now and come back to that kind of thing later? Okay, so then you got potential energy. Potential energy is the energy that is stored and held in readiness to do work as a result of an object's position or shape. So then you get two types, right? You've got the first type is gravitational, and it depends on the object's height or elevation or however you want to say it. And then you have elastic potential energy. And it is the energy of an object that is stretched or compressed. All right, so look at where it says gravitational potential energy in the box. You see the one in the box? Where it says gravitational potential energy is the energy stored in an object due to its position above the Earth's surface. Would anybody like to try to read that formula, replacing the variables with words? Go, Jack.
So it's the second one, gravitational.
Yep.
Okay. So it's gravitational potential energy equals mass, gravitational field strength, and height.
Right. So mass times gravitational field strength times height, because if there's nothing between them, it's always times, right? Multiplying. So here's something to think about. You see how mass is involved there? All right, I want you to pretend that you were standing on the railing out there like a crazy person. Nobody would want to do that, right? And next to you is a mouse, and on the other side of you is an elephant, and you're all going to jump at the same time. Which creature out of the three of you is most likely to get injured?
Wait, there's
An elephant, a mouse, and you.
The elephant easily.
Yeah, why? What does the elephant have?
It has more weight and
Mass, more mass. So when you increase the mass, you increase the gravitational potential energy.
I'd rather land on the
trying to
elephant
use
than
its
the other
ears.
one.
All right, now wait. So look at that. So look at the formula.
Shh,
Drew, look at the formula. So you're multiplying mass, gravitational field of strength, and height. Okay, so height. All right, think about this for a minute. If you were standing on a chair versus standing on the roof, which is the more dangerous fall? If you fell off the roof, because now you have most dangerous.
I thought you said that.
Because if you fell off the roof, you've now increased your height, and you're multiplying height times the other things in your formula.
That's on my land.
But no, still gonna hurt you. So
Yeah.
then, lastly,
unless you roll out, it actually makes the kinetic energy in a longer space of time.
So this-
instead of just
okay,
like
wait a minute, wait a minute.
that, catch you and say, you're not down on my
all right, so let's look at this last one. What's the last variable there? We did mass and we did height. What's the other thing that can be multiplied in there? What's G? Did we see G? What's G in that formula? Yeah, not grams. Look in the box. Under G, what's G?
Gravitational
Yes.
field.
Gravitational field strength. Okay, so you are standing on the surface of the earth and you're gonna jump off a 20-foot ladder versus you're in some magically tall, newly invented chamber in a space capsule and you're going to jump from 20 feet. Which situation is gonna cause you the most injury?
You're well, if
On
you-
Earth or in space? Wait a minute, just
technically,
answer one or the
you
other.
could be on the first line of the ladder.
Yeah, no, I said 20 feet. So
you said on a 20 feet.
don't nitpick, you know the point. So are you gonna get more hurt jumping 20 feet on Earth or in space?
You probably smack around in the chamber.
What do you think?
Space.
On Earth, why? What's greater on Earth?
Gravitation.
Gravitational. So anytime you add those three things, mass, gravitational field of strength, or height, any of those things that you increase, you're increasing the entire gravitational potential energy, right? Because you're multiplying them all together. So if anything you multiply is going to make it bigger. So look at the next one. That's elastic potential energy. It's the energy of an object that is stretched or compressed. Okay, now this gets a little weird in here. So it says elastic potential energy is the energy stored as a result of deformation of an elastic object. For example, the stretching of a spring. So K here, it says, is the spring constant. That you got to figure, and that's usually something you can gather when you're doing this information. But it's it's like you have to think about a spring. Think about a really tight spring versus a really flexible spring, right? And then you're also dealing with extension. What does extension mean? What do you think that means there?
I'm guessing it means the further you
How far you stretched it, right? And then that's what's going to give you your elastic potential energy. So you can use this for like a pogo sticks. You ever seen pogo sticks?
Yes, I
Where
want
they
one
jump
so bad.
on a pogo stick? All right, that's a great example. Shocks in your car are springs,
Sharks,
right?
pigs,
And then also, stop.
who's left?
And then he's quoting a movie. That was good. All right. And then
Curious George.
not Curious George.
I
Have
know.
you
that's
ever
Curious
seen
George. That's Curious George.
True. Have you ever seen hunters used to use, sometimes people still do them. They set up snares, tripwire snares and stuff where you use like a tree branch that you bend way down, a nice bendable tree branch. You ever bent a tree branch down and let it go?
Yeah.
Or been worse than walking through the woods and there's a branch in front of you and in front of the person in front of you, and the person in front of you pushes the branch like this and walks through and lets it go? What happens to you?
Yeah.
Right? Right?
I hate when that happens.
Yeah.
I
They've
hate
just
it.
they've taken all that energy they got from the food they ate that came from the sun, and they've pushed it and created elastic potential energy and smack you in the face.
And they created broken glass.
Yeah, there you go. Some forms of energy are mechanical energy, thermal energy, chemical energy, electrical energy, electromagnetic energy, and nuclear energy. All right, we need to run through this next section. So why don't you, from your notes, answer together, okay? So what's the first blank? What kind of energy? So we're at the top of page 4. Yeah, everybody together. What is it? Mechanical energy. Do you have it? Is associated with motion and position. What's the next one? Thermal energy is the total potential of kinetic energy of an object's microscopic particles and is associated with heat. So when we start talking about heat and temperature, you have to remember that the temperature is how fast the particles within a substance are moving. And the heat has to do with the transfer of that temperature. What's the next one? Chemical, right. Chemical energy is stored in chemical bonds. What's the next one? Electrical energy is associated with electrical charges, and that has to deal a lot with electrons. And what's this next one? Electromagnetic energy travels through space in the form of waves. Is there electromagnetic energy in this room right now?
Yes.
Oh my goodness, everywhere, all the time. You're being bombarded by it constantly. There's light waves from the sun, and then there's radio waves and microwaves and all kinds of waves.
Microwaves.
Everything you see,
Waves.
wait a minute, yeah. Everything you see is due to electromagnetic energy, because we can see part of the electromagnetic spectrum that we call visible light. But there is all kinds of stuff that our eyes cannot perceive that's out there bouncing all around. And what's the last one?
I guess it's nuclear.
Nuclear energy is stored in atomic molecules, atomic nuclei. Okay, I have a rule. The word, I've left my thing over there. 1 second, Jack. The word, this is my rule.
The bird. What is it?
Oh yeah, color, daddy today. This is the word. Look. In the middle of an atom, you have
You don't even know the words.
You have what? The middle of the atom is called the nucleus. So when you're dealing with that kind of energy, it's called
So what's in the center of an atom?
nuclear. Think about it as it's new and it's clear. What I will call you out for every time is if you do this.
What was that thing that we remembered that Felicia will die?
If you do this, I will call you out every time. What is this? Nuclear.
Let me see.
No nuclear.
No
nuclear. Nuclear is not allowed.
Nuclear.
I will call you out every time.
Nuclear.
A certain former president was famous for that, and every time he did it, I was like, oh, somebody correct it. And
Like, oh,
I didn't have anything against the guy personally, not too much at least, but he needed to stop it. Bush did it every time he said the word nuclear. He said nuclear, and I was like, somebody stop him! He sounds like an idiot. So anyway,
like you're embarrassing all the science.
How does that spell?
nuclear.
All
right.
Okay.
Moving on to the next part. No. Nuke is, if you abbreviate. Did you have something to say real quick?
Well, it's like when we were talking about what she did to make the Newton's cradle. It's like it was thermal energy from the core to that to the.
It's all
when
different
she
concepts.
ate
Yeah. Absolutely.
And mechanical energy in her bones to make
Right.
that go.
It is. So that's exactly what we're talking about in this next section, which is energy conversion and conservation. Does everybody see that? All right. Energy can be converted from one form to another. Energy conservation is the process of energy conversion, is the process of changing energy from one form to another. It's just converting it. One form to another, which is what Lily just did. Yes, we just observed it. Yes.
Very subtle.
Most forms of energy, she's napping. Most forms of energy
Yes,
can
you
be,
were.
most forms of energy can be converted into any other. Most, okay? So if you look at the graphic there with the frog and the car, it says the gravitational potential energy of an object is converted to kinetic energy of motion as the object falls. So I don't know what the next sentence is supposed to say this about a waterfall. That's a messed up sentence. The water at the top, think about a waterfall, I believe is what it's supposed to say. Oh, nobody caught that one? That one's out. Oh, you did? Think about a waterfall. The water at the top has what kind of energy? The water at the top of waterfall, what kind of energy does it have?
It has
Yeah, it's potential, gravitational potential, yeah. As it falls, it becomes what kind of energy?
Kinetic.
Kind of kinetic energy. All right. Now imagine there's a miller who lives downstream from the waterfall. He's going to take advantage of this now fast flowing water to build a water wheel. You see what a water wheel is, right?
Yeah.
Look that up, whatever that is, Drew. It's those things, they turn real big, right? All right. So he's got a big water wheel, and the water that comes by turns this big water wheel, right? So that's what they do. The water wheel takes advantage of the energy of the moving water, the kinetic energy of the moving water, and it turns a series of gears and mechanisms, and they're going to transmit the water's energy down to a millstone. You ever seen a millstone? They're big, flat, disc-shaped stones. Sometimes they're like this big, sometimes they're smaller. They're usually pretty tall, and they have like striations or lines on them and a hole in the middle. And the stone turns against another stone, and that's how they grind the grain, right? One rock against the other. So where did the initial potential energy come from?
The water.
The water, yeah, coming from the top of the waterfall. So how'd the water get to the top to begin with?
By probably another river at the top of a very, very high.
Libby would say it's a really, really high mountain. Where would the water have come from?
Probably the rain then.
Rain, right, or
The
snow.
melting snow.
All right, so if it's rain or snow, then how did the water get up there to begin with?
The clouds.
Yeah, how did it get to the
Jesus.
cloud? No,
Jesus.
stop. How did it get to the cloud from the ground? Think of your water cycle. How did it get up there?
Got up there by people throwing crap on the
No, Drew, stop. It evaporated. So what kind of energy do you need? Hang on, what kind of energy do you need for something to evaporate? What do you need?
Thermal.
Thermal energy, right. So the thermal energy is going to cause it to evaporate. Then it's going to get up in the sky. It's going to lose heat, condense, and then what's going to happen?
It's gonna get too heavy,
And then what kind of energy? It's got potential energy now because it weighs too much mass. It's going to fall. Right. Very good.
And then
All right.
I feel like I know.
Let's go over this last little bit. I'm just going to read, and I want you to follow along and make sure your answers are all filled in, okay?
Okay.
According to, we know that energy from the mill does not disappear at the millstone because of the law of conservation of energy. According to the law of conservation of energy, energy cannot be created or destroyed. The energy from the mill, from the water wheel, from the river, from the waterfall will always exist, but it will continuously change form as it's transferred to do work. Imagine the millstone grinding away stone against stone. If after time spent grinding you could touch your hand, that's a typo too, touch your hand to the stone, how do you think it would feel? How do you think it would feel?
Soft.
Soft after it's been grinding all this,
Warm.
yeah, warm.
I think it would be kind of.
It would be
soft
warm.
because it would work as like a sandpaper thing.
Yeah, I'm talking about the fact that it would be warm. It would be warm because of friction. Very often, kinetic energy is converted to thermal energy due to friction. This is why no machine is 100% efficient, right? It's not possible, right? Some energy typically leaks out of the process in the form of heat and then disperses into the atmosphere. So if you're in a machine shop where there are moving parts, even if they're well oiled, it's still gonna get hot, right? There's a lot of friction going on. So energy conversion, using less energy, or using energy more efficiently is called energy conservation. And that's not the same thing as conservation of energy. Conservation of energy implies that it's never goes away. There's just changes form. But energy conservation means using the energy you have wisely, like conserve water, conserve electricity, okay? Usually those things wouldn't mean
That
something
stuff
different.
costs money.
Yeah. So energy conversions and fossil fuels. Potential energy is stored in fuels such as coal, petroleum, natural gas. So we call these fossil fuels because they were formed hundreds of millions of years ago. So what's the little logo there that I put in your notes? What is that?
I said, when you said you get this logo, I'm like, yes, it's the Cars movie Dinoco.
It's Dinoco from the Cars movie. But what's in the picture? A dinosaur, because the fuel comes from,
Fossil fuel.
yeah, predominantly it's plant life. That's most of it. Most of it's plant life. It's you know, swamp plants and all that kind of business, okay? But still dinosaurs. You ever seen Sinclair gasoline? Sinclair.
Oh yeah, it's also got the same.
It looks very similar. It's got a green, like Brachiosaurus looking like thing, or a Apatosaurus on it, whatever. So those living things, if animals, guys, got their energy from eating other plants, if plants, they got it from the sun. Fossil fuels contain energy that came from the sun. Fossil fuels can be burned to release the potential energy stored millions of years ago. Power is the rate at which work is done. What's the formula for power? Somebody tell me. Work divided by time is power, right? The SI unit for power is what? Watts. Okay. Why? Somebody tell me why we call them watts. Who wants to tell me the watt story? How do we get to watts?
Isn't that a guy's name?
Oh, yeah.
It is. Go for it, Jack.
It was James Watt in
Uh-huh.
in 1776 or
1700s. Yeah.
Yeah,
Uh-huh.
1700s, where he was trying out his steam engine, and he referred it to the horsepower.
Right.
And horsepower, 1 horsepower equals 746 watts.
Right. Which is very arbitrary, right? It doesn't-
randomly think of
He kind of did.
746.
He
Alright,
sorta.
that's the number for
So
it.
basically, he produced this machine, all right, and he wanted to be able to explain to people how much power the machine could produce. But there was no basis for comparison. So he used a horse, because that's what most people will use then for power. You use your horses to pull your plows through the field, right?
Yeah.
So he used a horse, and he just kind of randomly decided that when the machine put out 476 units, which he was calling after himself, that it was about the same as 1 horse. So about how many horsepower do a lot of cars have? Does anybody know?
200.
Or,
Do you know?
or like 300.
It depends on the car. Yeah, like,
But,
yep.
Like, it was like how much horses could pull for like 33,300 like pounds or something.
mm-hmm. Yeah, exactly.
It's actually really cool.
It's the little, hang
because
on.
the fastest cars have over 1,000.
Yeah, so the big long graphic on the side of your page explains the whole story. It says it's usually defined as 33,000 foot-pounds of work per minute. A foot-pound would be like a Newton meter, but it's not in metric, it's in imperial.
Americans again.
Yeah, foot-pound. And there's a picture of James Watt, and it says one horse can move 330 pounds, 100 feet for 1 minute. and that 230 pounds, 1,000 feet in 1 minute, or 33,000 pounds a foot in 1 minute. And that is roughly what a horsepower is. So like my Mustang has 289 horsepower.
Woo!
Yep, and
It's funny because the symbol is actually a horse.
so real quick, let's raise your hand if you want to answer so we can be efficient with our time because it's time to do lab, but I wanted to get some answers to what you think would be good answers for homework questions. So explain why it's a good idea to conserve and not waste energy. Who has an answer?
Oh,
Any
I have
answer?
an answer for that.
Your hand's up, so go ahead and tell me.
It costs money. Is one.
Because it costs money, okay?
It costs money. It's limited.
Yeah,
Everything is
some of it is. Well, certainly fossil fuels,
Everything is limited.
Okay, go ahead. Well, not sun, but go ahead.
Yeah,
Or wind.
No, it explodes.
Well, it's not. We're not losing it today. Anyway, those are good answers. All right, who can raise their hand to tell me what does the law of conservation of energy state? Jen.
Mine had it written down. And I
Okay, well, what can you do off the top of your head? You know?
I put mine in the figure. I don't know.
That energy,
Cannot
It
be.
says energy cannot be
Created.
created or destroyed, only changed.
wait, I was calling him though. Don't
Oh,
interrupt
sorry.
others.
Thought you were just-
All right, last one. Oh no, two more, sorry. So who can give me 3 examples of fossil fuels? Who would like to do that? Anybody different? Eleanor, you look like maybe. No? Delia.
Type
3 fossil fuels, who can do it? Go for it.
I think it says here
hmm
coal, petroleum, and natural gas.
Perfect. Coal, oil, natural gas. Perfect. And why are they called fossil fuels, Delia?
Wait, coal is a fossil fuel?
Yes.
They are formed over hundreds of millions of
Yes.
years.
Good. All right. And our last one. Who can describe for me the difference between kinetic and potential energy? Go for it. Wait.
Thermal energy is the total petroleum and kinetic energy of an object, and chemical energy is stored in chemical bonds.
Can you tell me the difference between kinetic and potential energy? That's a tricky one.
I can.
Wait a minute. Let Eleanor think. Think about it with the ball. When we had the ball up high, it was potential. And when we let it go, it was kinetic.
Potential energy, as it falls, it becomes kinetic energy.
Perfect. Good job. Thanks, Delia. All right. You guys did really, really well. Excellent. Okay. So if you still have your questions in your binder, be sure you put them up there. Get your lab out. Put your name on it.
Where's the lab?
Staple it. Should be right there. Should immediately follow your notes. Yes, ma'am. I know everybody's. You can just write, hey, look, you answered. Or some of those have, like, you can still write answers on these. Like the ones that say very, yeah.
We only need 2 pages, right?
Why does it want
I think it's just 2, yeah.
And it was with can I please borrow a pencil?
All right.
Can I borrow a pencil?
Sure, sweetheart. There's some up there on the counter, I think.
That's really hard not to laugh at that.
That's it. Yep.